Today we'll discuss on hyperspectral remote sensing. Basically in the lecture we'll talk about what is the basis behind hyperspectral remote sensing, the fundamental behind it, and what are the sensors available in the image acquisition mechanism, sensors available in this, and the potential application from hyperspectral datasets. So as you all know from your fundamental lectures in basics of remote sensing, that when the light interacts with the Earth's surface, these 5 mechanisms can happen. Either the light gets scattered, it is reflected, absorbed, and emitted. What is there? It can be scattered means the light, when the energy falls on the Earth's surface features, it gets scattered in many directions, not only in the return back but in all other directions away from the object, so it can be scattered. The other is the light can be reflected, that the energy strikes the object, it can reflect away in a single direction. When it reflects away in a single direction, then we call it as a reflected energy. When it gets scattered or reflected in many directions, then they are scattered, they don't, and the other is it gets absorbed. As the energy strikes the Earth's surface feature, it gets absorbed and stored within it, which is usually considered as heat, and this energy, or what we say as thermal energy, always flow from warmer to cooler areas, and this thermal energy can be transmitted or transferred in 3 ways: conduction, convection, and radiation, and it can emit or radiate itself later on. So as the energy strikes, this absorbed energy which is absorbed can be emitted or released at a later time, and this energy can be measured during both daytime and night time. And lastly, the energy which is falling on the Earth's surface can be transmitted, or it passes through the object and can be changed or refracted. So this is what is there. So in summarize, if I say the energy from the sun reaches the Earth's surface, it's either absorbed, which is later on emitted, reflected, or transmitted, right? The reflection of this energy, if we will consider only the reflected component, then the reflection of the sun's energy by any material creates a unique footprint that you already know from the basic lecture, which is known as the spectral signature of the material. So it's a unique footprint which enables us. So the location and shape of these unique footprints, this reflection, absorption, enables us to identify different types of the land surface features, right? So if I look at it, you've all seen these are the different kinds of satellite images which you have already seen or interpreted in the previous exercises. A panchromatic image, a true color image, and a false color. So panchromatic image is what? It has a single band, one band data sets, black and white, whereas this is a normal color photograph which you can click from your normal cameras, RGB images. So true color images, this also falls in the category of multispectral because it has more than one band data sets. Then we talk about the false color, that is we are using the wavelength region which is invisible to human eye. We are moving on to the infrared region, which we call as and we can use the infrared along with the visible region to create a false color image. Now what we look at this example, why we need hyperspectral, or what is the significance of hyperspectral. Now if I look at the Landsat 8 bands, now in this Landsat 8 data sets, there are 9 bands. Now if you look at these ones which is highlighted in the pink color, here if you look, there is a coastal aerosol bands. Each of the band there is a wavelength region which it is associated. For example, coastal aerosol is from 0.43 to 0.5. Band blue, which is 0.45 to 0.51. Now each of them have a variable spatial resolution. Panchromatic with the high spatial with 15 meters, the others are with 30 meters. Now look at the bandwidth. Bandwidth is what? the difference between the range. This is the range. Bandwidth is nothing but difference between 0.45 minus 0.53. What is the band range? Now, this range is 0.02 in case of band 1. Others it is 0.06, and if I go to the shortwave infrared 2, it is 0.18, 0.18 and 0.02 again. So these are, if I convert it into nanometers, this will be 180 nanometers. 0.18 would be 180 nanometers. That means my bandwidth is large. It's a coarser bandwidth. Panchromatic bandwidth is 180 meter. Whereas here my bandwidth is around 0.02 would coincide to be 20 nanometers. Very small bandwidth which comes out in the some of the wavelength parts. Here it is 60 nanometers. So you all are aware about what is spectral resolution. Spectral resolution is basically the number of bands, but it is not only the number of bands, it is associated with the band range, spectral range, bandwidth. Smaller the bandwidth, better is the spectral resolution. Larger the bandwidth, coarser is the spectral resolution. Now what is this advantage? For example, in this case of Landsat 8, they introduced the band for cirrus cloud detection, which is band 9, which has a very narrow bandwidth. Now why did they introduce this? Now if you look at this image, I hope it is visible to you. This is the visible image and this is the band 9 image. Now here if you see, this band was created primarily for detection of high altitude clouds. The reason being that, and the wavelength region which you see is what? It is 1.36 to 1.38. Now this small bandwidth in this region around 1.38, this spectral band is designed to detect high altitude clouds, as this band, this small region, the region centering around 0.36 to 0.38 corresponds to a strong water absorption band. It has a very strong water absorption region, and it is so strong that any photon which is emitted by the sun cannot reach the earth's surface. And even if it is emitted, it will be again absorbed, it can never reach the sensor. So in this wavelength region, what will happen is earth features cannot be visualized, because the energy in any case cannot reach the earth's surface because of a strong water absorption zone. There is a water vapor present in the lower strata of the atmosphere, so it will absorb the energy, and whatever is reflected also gets absorbed. So nothing reaches the sensor, so the earth's surface will appear dark. Now what happens in high altitude clouds? High altitude clouds are at such an altitude that the reflection from this will never get absorbed to that extent, and it will reach the satellite sensor. So what is happening is, in this region, in the visible or the infrared region, what you observe is low altitude clouds are seen, but the differentiation between this high altitude cloud is not visible here. These are the cirrus clouds, even this area, which is not visualized in the other bands. Whereas in the cirrus cloud, because it is observing in a very narrow region which corresponds to a very strong water absorption surface, you will see that these clouds become distinct. So detection of cirrus clouds, it's possible. So the reason for hyperspectral is to go towards narrower and narrower spectral region, so as to able to identify certain objects on the Earth's surface, to enable us to strengthen to identify features. If the same data, instead of 1.36 to 1.38, it would have been 1.2 to 1.4, then what you get, the energy which is measured in the broad region is an average reflected energy, average energy from the entire region of the spectra. So this minute absorption band will not make much impact. You will not be able to detect the features. So in order to have use the property of the water absorption band which occurs in a very small region, I need to design sensors or features which are bands have observation in regions which are narrower in nature. So that is the reason why hyperspectral came into being. So hyperspectral, this is another one example where you have the RGB image between the band 654 of the Landsat, and this is the cirrus cloud image. So you can clearly see the other land surface areas are totally dark, whereas the cirrus cloud region appears totally white because of high reflection from them. The other areas, due to the water absorption, energy gets absorbed, nothing reaches the sensor. So this is the significance. Again, if you look at here, this is the difference between multispectral and hyperspectral. That means spectral resolution is higher in terms of hyperspectral, that is narrower band observations. So if I look at this observation from a hyperspectral sensor, I can reconstruct my feature. The reflectance curve is something very similar to the one which you read in your literature. Whereas with multispectral, since I have observed in 3 bands, I have 3 observations. Another example with Landsat, which has more bands also, this is the complete profile of vegetation which I can reconstruct by making observation in narrow spectral bands, which gets lost out with the coarser or the multispectral observations, right? Now ultimately what we can say, hyperspectral imaging belongs to a class of technique which is referred to as spectral imaging or spectral analysis, because it's basically a part of spectroscopy. It is collecting and processing of information from across the electromagnetic spectrum, and from 3 bands to larger number of the bands, more number of bands, in hundreds of bands is what is hyperspectral remote sensing. 3 broad bands to hundreds of narrow bands, right? So it's a continuous, it will give you a complete reflectance spectra can be obtained by the hyperspectral observation. So in a way, it is a combination of 2 technologies, imaging technology and spectroscopy, in a single system where it is used to create, acquire large data sets, and requires, hence when you have larger observations, larger data sets, then it requires new processing methods. And if you look at it, hyperspectral is basically requires narrow bands and contiguous bands. If there are gaps in bands, the continuity of observation is lost. I may have 20 bands here, but then on one band here, 21 here, 1 here, 1 here, 1 here. I'm missing out the critical regions. So contiguity between the observations is also necessary. So not only the narrowness of the observations, but contiguity. So this is, in a way, it summarizes what is broadband remote sensing, multispectral remote sensing, hyperspectral and ultraspectral. So if I say this is my panchromatic, the entire visible region falls into one, we make one observation which is my panchromatic region, this is broadband. Multispectral, the same visible region is broken down into 3 broad spectral channels, which is 0.45 to 0.52. It can be different depending on different sensors, it will be variable, but more or less it is dividing into 3 regions. Then the same visible region is divided into 100 spectral bands, and later on with ultraspectral, which is one step ahead of the hyperspectral, is thousands of bands within the visible region. So if I look at only one part of the spectra, that is a visible, 1 to 3 to 100 to thousands. So here multispectral is separated spectral bands, no spectral gap. This is what I meant by contiguity. There is no spectral gap between the observations. This is broadband, where my bandwidth may vary from 60 to 100 nanometers. This is a narrow bandwidth, where my bandwidth is of the order of 10 to nanometers or even less than 10 nanometers. Right? Coarser representation of spectral, it provides, multispectral provides a coarser spectral representation of spectral signature. What we saw, we had only few observations. whereas hyperspectral provides a complete representation of the spectral signature. And if I talk about the levels of spectral information, what it will lead, why do we need, where it is can correlate it. Now let us talk about panchromatic. All of you have seen a panchromatic image. What you can do, you can detect the presence of material which determines the presence of an object, activities or event, but two objects may have a similar kind of a appearance. So how to distinguish or classify or separate? Then you need multispectral, and so on you move towards the hyperspectral. So as the spectral capability increases, your power of analysis also increases, or what kind of information you can extract from this also increases. For example, in primary case, if I talk about panchromatic multispectral, it is just detection. The presence of materials, objects, activities can be done. Then next is when you have more information, you can classify them into spectrally similar groups. Then you can discriminate between two type of features. This is dense forest, this is sparse forest, or whatever is vegetation. You can discriminate between different categories as the spectral capability increases. Then identification of the material is possible. Then once, even with a more number of bands, you can determine the variability of the identified material, that is between wet and dry sand, soil particle size, snow grain effect size, and then finally you can quantify in terms of the abundance of these materials. So as the power of spectral information increases, your analysis or kind of information which you can extract also enhances. So this is what is there. Finally, what do you get? You have an image where for each pixel you can have large number of observations depending on the number of bands you have, and if using this information you can reconstruct this contiguous spectral signature, which you can correlate to the ground feature and identify the material present in the pixel. So this is another perspective of a three-dimensional hyperspectral cube, which is nothing but this is the spatial pixel x and y which you have in a multispectral, and in this case the z dimension is the number of bands or the wavelength. The wavelength is your z dimension, x and y is your position, and z is the wavelength. And this is another way of perspective of the this is single wavelength data sets, then hyperspectral, and this is the complete spectra of the pixel. Now another comparison between multispectral and hyperspectral. Now this is from the hyperspectral lab sensor. This is a MODIS data which has larger around 20 bands in 1 kilometer resolution. This is a Landsat image. So as the number of observation increases in hyperspectral, the fineness of the spectral signature you can observe, and from this it enables you to identify what that feature is on ground. Now if you look in this spectral profile, in this vegetation spectra, there is reflection and there are also zones where there is absorption. Now in this curve, which is more generalized with Landsat, lesser number of wavelength bands or MODIS, these peculiar absorption zones, they are missing. They are not captured. Now the main principle or the science behind hyperspectral is we identify, or these absorption zones which are there, they are typical of each and every feature on the ground. These zones where it occurs, the moment the composition of the material changes, the position of these absorption zones, whether it will occur, where it will occur, changes. And the absorption region is so narrow that it is missed out in the broadband remote sensing. So you can see it's a very, very narrow region and there is an observation here, but because of the broad observation, this small dip has been missed out. And this absorption is typical of that land surface feature. So when I make large number of observations, I am able to capture the region where this absorption occurs. And from ground reference, I also know that this absorption occurs for the X object. So I can directly say this pixel corresponds to that object. Right? So this hyperspectral sensors we said measure hundreds of bands, and most of the multispectral sensors measures only in few number of bands. So it's not the number of measured wavelength that defines a multispectral or hyperspectral. It is what? The narrowness and the contiguous nature. I may not have 100 bands, but if I have 20 narrow and contiguous band also, then also I can say it's a hyperspectral. So the main criteria to call it as a hyperspectral is narrowness of the band and contiguous nature of the band. So even 20 bands which are 10 nanometer wide and contiguous in nature can also be quantified or called as hyperspectral sensors. Right? Now why hyperspectral? That's the reason which I just told you, that to detect the absorption features. Now these absorption features are known as diagnostic features and are typically very narrow in region. And the surface material on the Earth's surface can be identified by the use of these diagnostic absorption features. They occur absorption occurs in an object because of the material present in it. Like when I said in the region of 1.36 to 1.38 micrometers, the water vapor present in the atmosphere absorbs the radiation. Similarly, the material present in the object absorbs the radiation. So where this absorption, each object, if I talk about minerals, is composed of either hydroxyline, carbonate, sulfates. So when they interact with the electromagnetic radiation, there is reflection and absorption. And the absorption points are very narrow in region, and where they occur depends on the type of composition of the object. Now if you look at this, there are two spectral profiles specifically in the region. It's been zoomed out in the region of 2 to 2.4 microns. Now if you look here, that the kaolinite and the alunite have an absorption feature at 2.1 and 2.3, right? But the feature has a different shape and position. It's a different shape, and the position of these absorptions are also separated out. If I talk about broadband remote sensing, multispectral, my observation would be with a 60 nanometer bandwidth. Everything will fall into one, and this difference in the dip region would be missed out. So here the bandwidth is how much? 20 nanometers. Difference between 2.1 and 2.3 is 0.2. So it will be around 20 nanometers here, and it will be easily detectable. So here if you look, this is if I can measure the amount of the dip and the width of the dip, because in the previous case also you saw the amount of the dip, the shape and the position of this dip is totally different. So and they are characteristic of each of the mineral. So kaolinite and alunite, it is characteristic of them that the dip would be in this case 2.1 microns, width will be this much, depth will be this much. And using this information, measuring this information, I can characterize from the data what mineral it is there at that location. Some of the absorption zones, like if you see in iron oxides, they are broader in nature. Compared to the previous one, they are narrow absorption zones, whereas in iron oxide materials, these absorption zones are broad bands, and hence they can be easily identified by the multispectral data also. The absorption bands which are very narrow in nature require finer observations. Now this is one. The absorption is due to HOH bond, that is hydroxyl bond here present in this. Because of these absorptions are there, they are also at certain locations very narrow in nature, and to capture it you require fine observations, that is an hyperspectral data. This is for a vegetation species of pine and fir. As you look, they are very close to each other. The depth is different, but the position is very close to each other. If I make a broadband observations, this location would be missed out and both the profiles would appear similar. It will be hard to identify whether which is pine and which is fir. So in order to identify these two features, I need finer observations. Now, what is the wavelength region? This anyway, some of it you had in the remote sensing lectures, where in case of which wavelength is suitable for what kind of applications. In terms of hyperspectral remote sensing, because of the material composition, 0.4 to 1.4 wavelength, in case of minerals, which is the feature which you are able to capture, that is iron bearing minerals. If it is there, carbonate and sulfate composition is there, then this is the crucial wavelength to look for. If the mineral contains carbonates, hydroxyl or clay, etc., then 1.5 to 1.85 to 2.5. So the short wave infrared region is crucial in terms of carbonates, hydroxyl groups, whereas sulfates, iron bearing minerals, as we saw in the previous example, that for iron oxide they are broader in nature, and specifically the red region is very important for iron bearing minerals. If I talk about vegetation features, then in terms of chlorophyll, differentiation, plant water content, cellulose, protein, starch, lignin, 0.43 to 0.65, the visible region, the near infrared and the short wave infrared are significant. Short wave infrared in terms of the water content in the plant. Then for the snow and ice studies, you have this for understanding the snow grain size, its impacts, effects, snow depth, contaminants, liquid water content, the visible region and the near infrared region is useful. Now, what should be the optimum requirement for the spectral bandwidth in terms of different applications? So, if you look at it from this, for different applications of vegetation, water, or in terms of geological applications like iron minerals or any other minerals, what is coming in all the wavelength region, whether we are talking about visible, near infrared, an optimum resolution coming out is 10 nanometers, because here in the visible region 20 nanometers, but as we go ahead it says 5 to 10 nanometers in the near infrared region. So, an optimum wavelength, if I can say, 10 nanometer would be appropriate for all kinds of vegetation, soil and geological investigations. In the short wave infrared region, again for different applications of soil moisture, for mineral identification, for different mineral carbonates, sulfates, all these features, an optimum of 10 nanometers is the one which is required for proper utilization of hyperspectral data sets for identification of these features. So, in a nutshell, we can say multispectral instruments can discriminate materials, whereas hyperspectral enables us to identify the features on the Earth's surface. So, the most significant advantage of but however, multispectral advantage is that many multispectral images are available. Hyperspectral, there are still very few number of space-borne hyperspectral sensors. Mostly they are airborne. And what is the limitations of hyperspectral data if we talk about? Since we have large volume of data, as we saw in the visible itself, you have large number of bands, so there will be redundancy. It is also very sensitive to noise. And the main issue is most of the hyperspectral sensors which are space-borne, they are of a moderate spatial resolution. So, in those cases, what do you have? You will get a mixed pixel effect. Mixed pixel is what? That when we have a coarse to moderate spatial resolution, for example, let us consider as 30 meter spatial resolution, within a 30 meter pixel, you will have many land cover features. And the reflectance which is measured, or the reflected energy which is measured, is the weighted average of the energy reflected by different objects within that 30 meter pixel. So how do I interpret to which class or what is the material on the surface? Because the spectra which I get is not from one material. The spectra is a combination of the reflectance from different material present in that large pixel of 30 meter by 30 meter. So how do I identify which is the land cover class? So this is one of the major problems with the hyperspectral datasets. Then hyperspectral datasets needs to be calibrated. You have atmosphere in between. Atmosphere interacts with the electromagnetic radiation. It attenuates the signal. So those kind of corrections need to be done with hyperspectral before it can be used for further analysis. So this is what I mentioned was the mixed pixel problem, where if you look, this is one big pixel. Within one pixel you have lot of variability, and that the output pixel is a combination of the different objects present within it. So data volume is, redundancy is there in hyperspectral datasets, and however it has its strength that if you have done all these corrections onto the datasets, which we will discuss subsequently, then it will give you information where it enables you to identify features on the Earth's surface. Now, as in case of multispectral, hyperspectral remote sensing can also be acquired using whisk broom, push broom and frame camming system. So the entire whole principle is similar to the multispectral, except that once the light comes, the electromagnetic energy gets separated into distinct angles, and the spectra of the single ground pixel will be dispersed. This energy from here will be dispersed and dispersed using a prism or a grating instrument. Like a prism, if a white light passes through a prism, the light gets reflected into its various colors, its various spectra. So similarly here we have a grating instrument or a spectra which disperses the light into its respective wavelength, and then corresponding to each of these wavelength there are detectors which will record this energy, measure this energy and convert it into a image. So this is how is there. Energy from the ground gets scanned, falls on a dispersing element which disperses the light into its different wavelength. There are detectors corresponding to each wavelength. They measure the radiations and the image is composed. So these are the three acquisition mechanisms for hyperspectral sensors: point scan mode, line scan mode and the plane scan. Similar to a multispectra, we can say this is whisk broom, push broom and say area scanner. So a line by line the pixel is observed, falls on the optics where you have the dispersing element which disperses the energy into different wavelength and they are measured. This is a push broom scanner. So instead of one pixel at a time, this is a line which is scanned one by one to create this image, and in this case chunks of blocks, an array, area array is scanned and converted into the image. Blocks of images are scanned and the whole image is reconstructed. This is another perspective of it. What you see, it's a pixel by pixel scanning and line is constituted. This is a line scanning, area scanning and how you get the final hyperspectral images is acquired. Now what are the different, as we mentioned, hyperspectral sensors are more in specifically airborne cases. We have large number of airborne hyperspectral sensors, whereas less number of spaceborne. So we'll just see what are the different, and we have ground based instruments which are necessary in case of hyperspectral analysis, which are known as spectroradiometers. Now this is AVRS is one of the well-known, oldest airborne visible infrared imaging spectrometer, which has 224 spectral bands in the wavelength region from 0.38 to 2.5 micrometers with a bandwidth of 10 nanometers and a 30-degree field of view with a pixel size of 20 meters and a swath width of around 11 kilometers, and this is flown on an aircraft and hence can be flown under clouds, and depending, this pixel size can be varied depending on the flying altitude. You have another airborne hyperspectral sensor, which is HIMAP, hyperspectral mapper, which is having around variable 100 to 200 bands with a variable bandwidth of 10 to 20 nanometers and a variable spatial resolution, again depending on the flying height. Then from Calgary, this compact airborne spectrographic imager, you having 288 bands in the spectral region from 390 to 900 nanometers, so it's up till only the near infrared region, again with a variable spatial resolution of 1 to 10 nanometers. These are few more airborne sensors, HIDIS developed by the US Navy, digital airborne imaging spectrometer, which is an European airborne sensor, having variable bandwidths at variable spectral resolution. So if I talk about satellite sensors, these are some of the satellite sensors which are available. Hyperon, which is from US. NASA is the organization which launched this satellite with a spatial resolution of 30 meters, swath of a small swath of 7.6 kilometers, wavelength covering the entire visible and the infrared region up till 2.5 micrometers, 242 bands with a spectral bandwidth of 10 nanometers. Right? CRIS, compact high resolution imaging spectrometer, which is from the United States, launched by the European Space Agency. This has a variable spatial resolution at 18 meters and 36 meters with a swath of around 13 to 14 kilometers at nadir with a wavelength of 400 to 1050 nanometers, and they provide data in variable bands. So they'll give you 19 bands with at 18 meter resolution, 63 bands at 36 meter resolution, again with a variable spectral resolution. Then onboard, India launched onboard its Indian mini satellite IMS, a hyperspectral imager, which has a spatial resolution of 506 meters, swath of 129 kilometers approximately in the visible near infrared region with 64 bands and 10 nanometer spectral bandwidth. China also has launched one hyperspectral imager with 100 meter spatial resolution, swath width equivalent to 50 nanometers or more, variable from nadir to off nadir, then 400 to 950 again in the visible near infrared region with variable bands of 110 to 128, and the spectral resolution is 5 nanometers. The bandwidth is 5 nanometers. US has launched another one, HICO, which has a 90 meter spatial resolution, 42 kilometer swath, again in the visible near infrared region up to 1081, 128 bands, and 5.7 is the bandwidth. So this is the further specs or image from the Hyperion sensor. This is the Hyperion sensor. This is CRIS proba image, which gives you at a variable spatial resolution at 18 and 36. Another airborne sensor, which spaceborne sensor, which is medium resolution imaging spectrometer, which has the variable bandwidth from 10, 7.5 to 2.5 at variable wavelength regions, and a spatial resolution which varies from 300 to 1200 nanometers, again operating in the spectral range from 390 to 1040, and a sampling interval of 1.25 to 30 nanometers. This is for the HICI sensor of India, which I just mentioned. Onboard Chandrayaan also, India launched its hyperspectral imaging instrument, which has nearly similar characteristics with the IMS. except for the better spatial resolution of 80 meters. There the spatial resolution was 500, here it is 80 meters. Now these are some of the forthcoming or future satellite sensors in hyperspectral areas. They are from different countries, from Germany, Italy, South Africa, US, Japan, France and India, with a variable spatial resolution from 15 to 30 meters to 60 meters, and a coarser one which India is planning from a geostationary platform. So this will be one of a unique mission where India will place a geostationary satellite with a hyperspectral sensor providing you 320 meter spatial resolution in the near infrared and 192 in the shortwave infrared. And this will cover the entire spectral range from 400 to 2500 nanometers. And this is the Japanese satellite. They are also planning one hyperspectral satellite suite which will be launched in future with 30 meter spatial resolution and with 185 bands and a bandwidth of 10 to 12 nanometers. And in near future, this is planned NMAP from Germany, which is 30 meters, swath width of 30 kilometers, again in the region from 420 to 2450 nanometers with 218 bands and 5 to 10 nanometers, the spectral resolutions. Now we'll talk about the applications, the potential applications of hyperspectral vis-a-vis the multispectral datasets. Now if we talk about the major applications, mining, geology, forestry, agriculture, environment, what you can get from multispectral and what added information you get from hyperspectral. So if you talk about mining, geology, mineral, from MSS multispectral sensor you can do a land cover classification, whereas with hyperspectral you can go for mineral mapping, identification of different minerals on the earth surface feature. For vegetation application, forestry, again land cover feature, major or maybe to some extent more distinct classification to forest types, but with hyperspectral it leads to species identification, vegetation stress studies, detailed stand mapping, foliar chemistry can be analyzed with the hyperspectral datasets. In terms of agriculture, with multispectral, land cover classification, to some limited extent crop mapping, whereas with hyperspectral, soil mapping, crop differentiation and crop stress studies. So these are some of the few which has been mentioned, but more detailed analysis can also be done. Soil salinity, soil in this case, then environmental management. With multispectral you can have land use monitoring, whereas with hyperspectral chemical mineral mapping and its analysis can be carried out. So this is the strength of hyperspectral datasets. So here what is there, that with terms of imaging spectrometry, the applications for mineral targeting, the spectral region you have to use from around 300 nanometers or 3.3 micrometers to 2.5 micrometer with 10 nanometer bandwidth will enable you to help in mineral targeting. For soils, high resolution imaging spectrometry helps in genetic and fertility classification of soils. For vegetation, as we said, we have the ground potential. You can see, for example, here, this is the spectral profile, or you can say a spectral signature for a general vegetation features, and these are water absorption regions. But if you look at the region where if the vegetation is green in color, what will happen? It will absorb blue wavelength, red wavelength and reflect in green. So this is blue, green, red. Now after the dip in red, suddenly there is a rise in the infrared. This sudden rise is known as red edge of the spectra. So here it's the suddenly this sudden rise. So this is a position which falls around 670 to 740 nanometers, this red edge location, which will enable you to detect the around 670 to 740 nanometers, this red edge position is there. So depending on this position, you can identify whether the vegetation is stressed due to what, or it's a healthy vegetation. So this is known as, this is the red edge point, that is where the sudden rise in due to the infrared position dip to rise. Now if this red edge shift towards the lower wavelength, then we say the vegetation is stressed. If the red edge shifts towards the longer wavelength, then it's a healthy vegetation. Now this shift in wavelength, if you look at it in this point, this shift in this wavelength towards the lower edge is not too broad, it's very, very narrow. If I can measure this, or if I can identify this shift, I can lead to an analysis of the stress in the vegetation. What kind of stress, whether it is nutrient stress or for what reason, that can be correlated. So to measure this stress, which is very, very narrow in nature, hyperspectral satellite data, hyperspectral sensor data sets help. And with this we can calculate the red edge position, and depending on the red edge position, one can say it's an healthy vegetation or a stressed vegetation. So you can see there's a drastic rise in the reflectivity from around 10% in the red to more than 60% in the infrared. So this sudden rise is known as the red edge locations, and it helps in determining the stress or the healthiness of a vegetation. And this can only be captured when you make minute or finer observations, that is the in case of hyperspectral sensor, which is done. So this is another example which highlights a healthy plant. The red edge is towards a longer wavelength, and if it is shifting towards the lower wavelength, that is called as blue shift, which is telling you this is a senescence plant, that means dried out plant. So there is a stress. So this is how it can be used for monitoring the stress in the vegetation, and that reason of the stress can also be identified. Another application to vegetation is it can be utilized for mapping the burn scar. When fire occurs, the scars which are left can be mapped using the hyperspectral data sets. Urban applications, of course there is a limitation with the urban applications because most of the satellite sensors are having a coarse spatial resolution. For urban applications, what you need is very high spatial along with spectral information, and which at the moment is a limitation because most of the sensors are with more than 30 meter spatial resolutions. In case of airborne, these are some of the studies which has been done using the airborne visible infrared imaging spectrometer from the US, where you can say that the different types of road surfaces can be classified. So whether it's a pavement, parking area, concrete, all these variations, you can see there are slight variations onto their spectral profile, and the point where the absorption is occurring is differing. If this is captured, then the kind of the urban surfaces materials can be mapped. Then atmospheric studies, atmospheric parameters can be measured using a hyperspectral data set. Oceanographic applications, for example, this is one of the application for oil spill. Now if you look at the general profile, a reflectance pattern for the oil and the ocean water, you will see hardly there is a difference. Very minute differences there which cannot be captured with your observations from the blue wavelength onwards. Blue to some extent, but still due to scattering lot of problems are there. But when we talk about hyperspectral, there again with finer observations you will get these small absorption zones due to the oil material, and these are due to the carbon hydrogen bond at three distinct regions at 1.73, 2.3 and 1.2. So if I can measure this, I can find how much is the thickness of the oil and the concentration, whether it is in large amount or lesser amount. Right? So this also enables you to differentiate between the water surface, which is difficult with the multispectral, whereas with hyperspectral, oil spill can be identified. So this is one comparison of the classification done using different multispectral and a hyperspectral sensor, how it enables us to strengthen the classification. The number of classes which can be identified with the hyperspectral is much larger than the multispectral. But there are certain issues with hyperspectral, that in hyperspectral basically pre-processing is one aspect which is required, because hyperspectral sensors, there are a lot of data sets, there are small observations are done, you have noise present in it, there are other errors which needs to be corrected, their signal to noise ratio in the shortwave infrared is also lower, so some kind of pre-processing is done. Then atmospheric correction is required because I am correlating it to the ground spectra. So you need to correct for the atmospheric disturbances, atmospheric attenuation to get the exact ground spectra, and of course geometric correction to correlate to the spatial location on the ground. So these are with the Hyperion images, you see there are certain stripes available which needs to be corrected, that is radiometric, and this is a raw data. Without doing the atmospheric correction, the profile is different. This is the raw data without any atmospheric correction. This is after atmospheric correction. The profile appears very closer to the one which is the ground spectra profile. So these are some of the atmospheric correction methods which are image based and radiative transfer model based. These are relative in nature. These are absolute correction methods for atmospheric effects. So relative, approximate values, when you want to quantify something from the satellite data sets, then the absolute correction methods are preferred. Now in case of hyperspectral sensors, as we said, the spectra which is generated from the image is compared with the ground spectra. Now the collection of ground spectra is known as spectral libraries. They are basically references using which you are comparing the image spectra and trying to correlate the two of them and say this is this feature on ground. So they are nothing but the collection of spectra of different surfaces generated from lab and ground measurements, and they contain spectra of individual species acquired at test sites which are representative of different terrain and climatic conditions. So some of the spectra are also available on the website from the JPL NASA, USGS, from Astra Library. Many spectra are available, or you can collect it from your own ground instruments, your spectroradiometer, and generate a spectral library of different land cover features in that area. So this database enables in identification of materials by matching their spectra with the spectra obtained from the Earth observation satellites for identification of features on the ground. So these are some of the publicly available spectral libraries which are included in NV software. Astra Spectral Library on the internet is available. You can create your own. The mapping techniques, the classification techniques in terms of hyperspectral also varies, because the conventional multispectral data techniques doesn't work like a supervised classification, because the number of bands increases. There is a phenomena called Hughes phenomena which happens because of the large number of bands. Those methods are unable to classify such large volume of data sets, because of which new approaches are identified for classification of hyperspectral data sets. So these are some of the results using spectral angle mapper. It creates separate images for into the number of classes or the features you want to identify. So for example, this is a grassland. So all white which you see are grassland areas, urban, and accordingly all features are identified. Urban areas are white here, forest areas are brighter. This is the unmixing. When you have mixed pixels 30 meters, then in that case you can see that unmixing algorithms to what we mentioned, that for a mixed pixel it is difficult to correlate to a particular class, particular type of feature on the earth. So that pixel has to be unmixed into different classes present in it. So this is one of the method. Unmixing unmixes a pixel into its different constituents. and for each it gives you a separate image. This is a soil fraction image, this is a water fraction image, and this is a vegetation fraction image. These are some of the softwares which are available, which can be utilized to process the hyperspectral data sets. The NVE, Geomatica, ERDAS, hyperspectral processing, MATLAB is there, Multispec is there, TNT MIPS are there. These are some of them available. So with this we conclude the lecture.